In this lecture, we finally are going to talk about the interrupts. The last chapter about timers had plenty of theory with many references to interrupts already. In this chapter, there will be many practical examples. Basically, interrupts are an interrupting way to react to certain events. That means, if an interrupt is configured properly, the CPU will stop doing whatever it does and pays attention to the event that just occurred. After the CPU is done with processing the event, it will continue where it was left off. Especially in embedded systems, the concept of interrupts is exposed to the programmer. Those systems interact closer with the physical world in which events occur continuously and your system should react to. By the end of the lecture, you will be very familiar with the handling of those events. So what are we going to do in this chapter? First, we will start with pointing out the advantages of using interrupts compared to the alternative, that is, polling. Then we will talk about the interrupt subroutines, which are essentially functions that are executed when a particular interrupt occurs, and I'll show how to activate interrupts. Next is the interrupt vector table, which lists all possible interrupts and acts like a table of content, telling what to do when what event occurred. In conjunction with interrupts, it is unavoidable introducing a new attribute for data types, and that is volatile. What it is and what it does will be discussed in section 5. Further, we will talk about various interrupt sources, their priorities, and what happens if another interrupt occurs if a current interrupt is currently being processed in the section Nested Interrupts. Towards the end, we will talk about some mistakes in handling interrupts before concluding the chapter in a summary and outlook. Let's get started. In the previous chapter, we had this example listing in which we configured a timer and then continuously checked for a particular value to know when a second has passed. After that, the timer was reset, so essentially we implemented a timer in CTC mode. After that, we made the LED blink. Hence, instead of using the delay ms function, we implemented the same functionality using timers. However, this is a very inconvenient way and we cannot guarantee if the while loop is always exactly 1 second long. It might be a little bit longer as the CPU has to continuously check the value but also jump within the loop. This constant check is called polling, and we poll the value of TC and T1 in this example. It would be better if we could configure the timer in such a way in which the timer let us know if a second has passed. So we shift the blinking of the LED into a function called doSomething and tell the timer that after a second, execute doSomething. In the meantime, the CPU can do either something else or just sit there and wait. Wouldn't that be convenient? Let's see if that can be achieved somehow. For that, we have another look at the block diagram of the timer. We discussed the functionalities of those blocks in the previous chapter, except we entirely left out a few tiny details, and that is the purpose of those signals here called OCnA, OCnB, and TOVn with this int rec every time. That int rec stands for interrupt request, and we are going to use this functionality here. As said earlier, this line here is connected to the comparator of OCnA and TCNT, and it goes up if the values are equal. That means, for instance, here will be 3 and 3 will be stored here as well. This signal can be used as an interrupt request. Similar is the OCnB interrupt request. The TOV signal is slightly different. It is set when the timer overflows from max to bottom. Please note that this bit is not cleared by the control logic except when the TOV interrupt request is handled. So for the blinking LED example, what do we need to do? First, we will count to a specific value and reset the counter after reaching it. So we need the clear timer on compare match mode, or CTC in short. To count to 1 second and a prescaler of 1024, the OCnA needs to be set to 15,624. Then we wait till the OCnA signal goes up, since TCNT matches OCnA, and execute the do something function. So, without further ado, let's head over to the VirtualBox image and implement those tasks. You will find the entire program in the resources folder on the right, or in the directory course and then IRQ and blink in the VirtualBox image. I booted the virtual image, and let me change to the directory cd IRQ and blink. In this directory I have already the blinking LED program that we had earlier. So I'm setting the prescaler here and wait till the TCNT1 reaches 15,624, which is 1 second. Then I reset the counter and I make the LED blink. So I can compile and upload this, and the LED is going to blink. Okay, first task is to change the timer 1 mode from the normal mode to CTC mode. For that we have to know what bits to set in TCCR1A and TCCR1B. Since I do not know the bits any longer and where they are located, let me consult the manual, which I copied into the documents folder. Okay, let's go to the table of content, and there must be somewhere timer 1, that is here, and register description. Okay, here's WGM11 and 10, which is in TCCR1A, together with the COM1A and COM1B settings, but I need the CTC, and here we are. So for the top value in OCR1A, I just have to set WGM12, which is, if I scroll down a little bit further down, in TCCR1B. In addition, I just check if I set the prescaler correctly in CS12 till CS10. For that I have to scroll down a little bit further, and I want to use the prescaler 1024. That means CS12 is to be set and CS10 is to be set. Okay, with that information, back to our program. That means we have to configure TCCR1B, B2, BV, and then WGM12, which means CTC mode. In addition, these are the bits for the prescaler. And if I want to run it in CTC mode, I also have to set OCR1A to 15,624. Okay. Also in the lecture, we already created a function called do something. In which we made the LED blink. And since I activated the CTC mode, I don't have to do the polling any longer, and I don't have to reset the TCNT1 anymore. Okay, now the timer runs in CTC mode, and every time when there's a compare match, 1 second has passed. What I have to do now is I have to tell the timer somehow to execute do something whenever the compare match happens. To do so, and explained in a minute or two later in the course, in the next session, we set a timer mask of timer 1, and we activate the local interrupt of the compare match. It's on compare match, interrupt enable of timer 1 and unit A. In addition, I have to activate global interrupts. Don't worry, these two lines will be explained in a minute or two. Further, so far, an interrupt is going to be executed, but still the ATmega 328P does not know that this function is to be called when an interrupt occurs. To do so, I have to use an interrupt subroutine. Interrupt subroutine, and as a parameter, it takes the kind of interrupt that is going to be executed. In this case, it is timer 1, compare, unit A added by vect. This is essentially a function that is called whenever the interrupt happens. And in this function, I execute do something. ISR, the meaning of it, and how to derive the parameter will be explained also in a minute or two. As a further optimization, as you can see, do something is very small. It probably contains only 3 instructions. That is loading port B, XORing it with this value, and storing it in port B again. To make sure that the compiler inlines this line into the ISR, we can instruct the compiler to inline this function by writing inline static in front of it. This is just an optimization in case the compiler does not inline the do something function. Okay, let's save it and compile it. Oh, I made a mistake. Here is an undefined reference to SEI, which, if you remember, is activating the global interrupts. And this was the local interrupts. This function is defined in another header file. So I have to include avr interrupt.h. Okay, let's try it again. And it uploads. And does it blink? In my case, it does. Congratulations, you wrote your first IRQ program, and in the next lectures we are going to talk about the meaning of these lines and especially the ISR. In the previous section, we implemented our first program that utilizes interrupt requests, or in short, IRQs. Some new concepts were used in that example, which we haven't talked about yet. So let's do that. First, the interrupt subroutine, or ISR in short. Instead of the do something function, we have to instruct the compiler that this particular function is to be executed when a specific interrupt occurs. It is not called anywhere in the software program. The kind of interrupt is specified in the parameter. Otherwise, how will a compiler and the CPU know if we want to execute a function on a compare match, and that too caused by which unit, A or B? Or maybe we want to execute that function when an overflow occurs. For that, in the parameter of the ISR, we give the desired interrupt. And how do you know the name? In the interrupt vector table, which we are going to talk about in a bit, and which is also attached to the resources folder, all interrupts and their names are listed. As a general rule of thumb, to derive the name, take the string mentioned in the source column, replace the spaces by an underscore, and add an underscore and vect to get the name that is put into the ISR. For instance, the ISR parameter timer1 underscore OVF underscore vect makes sure that the ISR is executed when an overflow in timer 1 occurs. Easy, right? But there is more. What if you like to execute the same ISR but for a different interrupt? The ISR does not accept two interrupt vectors as a parameter. It is quite simple by defining another ISR with the desired interrupt vector and define this ISR as an alias of the original ISR. Problem solved. Another special ISR vector is the bad ISR underscore vect, shown here. This is an ISR that is executed if an interrupt occurs, but there is no ISR available for this interrupt. Hence, the bad ISR underscore vect works like a catch-all interrupt subroutine. This is different from the code shown below. There might be a situation where the definition of an ISR is useful, but you do not have any content. So you can define it as an empty interrupt. If that interrupt occurs, nothing happens, but it is not a bad ISR either. Okay, that's all about the ISR for the moment. Next, let's talk about how we activated the interrupts in the example program that we implemented earlier. Let's talk about how to activate the interrupt. Every timer has a timer mask register shown here. The one for timer 0 has only 3 fields. 1 bit for the interrupt of compare unit B, 1 for compare unit A, and if the overflow should be able to cause an interrupt. Depending on which field is set, the interrupt is being activated. These are the local interrupt activation bits. But there is also a global interrupt activation bit, which allows to activate or deactivate all interrupts at once. For instance, if you execute a segment in your program which is not allowed to be interrupted under no circumstances, you can clear the I field in the status register asrec. If any interrupt occurs now, it is going to be deferred till the I field is activated again. After that segment is executed, you can reactivate global interrupts and the CPU continues with your program or executes the deferred interrupt requests. Please note that the default value of I after a reset is 0, so interrupts are deactivated by default. To make it easier for the developer to activate and deactivate global interrupts, two functions are provided, that is SEI for set interrupt to activate and CLI for clear interrupt to deactivate global interrupts. Both do not actually invoke functions, but an assembly instruction SEI and CLI. So there is no function overhead which can be interrupted again. One thing to note, let's say you have an overflow timer interrupt, but global interrupts are deactivated. If a timer overflow occurs, the interrupt is deferred and executed once global interrupts are reactivated. However, if the overflow event happens multiple times, this information of multiple events is lost, and when global interrupts are reactivated, the ISR of the overflow will be executed only once. That's all what I have for the interrupt activation. Let's talk about the interrupt vector table, or IVT for short. The IVT is essentially an address book, and here's how it works. Assume a local interrupt is configured and global interrupts are activated. Now an event occurs. Let's say it is the compare unit A of timer 2. The CPU then jumps to a fixed address in the program memory space. Conveniently, at exactly that space, the IVT is located. It is always the same addresses for the IVT entries, and they have been essentially hardwired in the CPU. As you can see, the IVT starts with a reset vector at address 0. That means your program always and automatically starts with an IVT entry, and the first instruction is a jump instruction to the first instruction of the main. But back to the example. In this case of a compare match of unit A in timer 2, the CPU jumps to the address 0E. At this location is a new instruction which contains an unconditional jump to another address, which is the address where the ISR of the compare unit A of timer 2 starts. Since the program that we implemented earlier uses interrupts, let's have a look at the interrupt vector table in the image or in the resources folder. In the image, you can find the compiled program in course, IRQ, and then IVT. Okay, let's have a look at the interrupt vector table of our blinking LED program. For that, let's go to course, IRQ, and IVT. This is our blinking LED program with CTC and IRQ. Let's compile this, and I don't have to upload it because I just want to look at the ELF. Okay, the entire program is now in binary format in ELF, and it has to contain our interrupt vector table. To have a look at it, we use object dump and we disassemble it of ELF, and since the output will be long, I just use less. Okay, and here we are. At address all zeros, we have a jump instruction to 68, which is also called TOVn. And then we have bad interrupts up to address 2C, which says then vector 11. And it's a jump to address 80. Let's have a look at what 80 is. Vector 11, here's address 80, and here is our do something function. You can see the XOR here. This function then ends with a return interrupt at address A2, and at address A4 the main starts. Let's have a look at what bad interrupt does, which is at address 7C. Here's address 7C. So it contains a jump to 0, which is vectors. So when a bad interrupt happens, it jumps back to the vectors. And at address 0 is a jump to TOVn at address 68, which is here, which seems to prepare something and then jump to main. Hence, every time a bad interrupt happens, the ATmega 328 will reset. This is the entire interrupt vector table. Let's have a look at what vector 11 at address 2C means. For that, we go back to the reference manual and search for the interrupt vector table. (328p), and here we are. Timer 1 compare A is vector number 12 here. In our program we had vector number 11 because we started counting from 0. In this case then the vector numbers match. However, as you can see here, timer 1 comp A is located at program address 16 in hexadecimal format, while our program, the vector 11, is located at address 2C. Hence there is a mismatch. However, the addresses given here are so-called word addresses. Each address accesses 2 bytes, while these addresses are byte addresses. That means every address accesses 1 byte. Let's have a look at an example. At address 0, an unconditional jump to address 68 in hexadecimal format is written. This instruction translates into this byte sequence. As you can see, there are 4 bytes. Hence, the next available address will be at address 4, starting from 0. If I count the words instead of the bytes in this entry, I have 0C94, which is one word, and 3400, which is another. That means the next available word address will be 2, which is then mentioned here. Please keep this discrepancy in mind if you want to write your own interrupt vector table and remove those vectors, for instance, which are not used at all, optimizing the program memory space. That's all what I have about the interrupt vector table. Let's talk about the attribute volatile, which hardly exists in the world of personal computers, but which is essential in embedded systems. It is easiest explained by an example. So head over to the course directory and then IRQ and Volatile to see the purpose of Volatile in action. In this short demo, I'm going to show you the purpose of the attribute Volatile for data types. For that, we can go to course, IRQ and Volatile. I already prepared a little program that is again the blinking LED with CTC and IRQ. However, there are some changes. That is, I have a global variable called count, which is 8-bit in size and unsigned. In the interrupt subroutine, I increment the count. In the main, I set count to 0, which is actually not necessary because all global variables are initialized with 0 according to the C standard. I just did this for clarity. And in the while loop, I check if count is equal to 2, then I reset count and I make the port blink. Since I check the count equal to 2, the LED should blink every 2 seconds by now. So after 1 second, count is set to 1, and in the second, count is set to 2, and the LED will toggle. So let's see if it works. First I clean everything, then I recompile it and upload it. As you can see, nothing is blinking here. And the reason is not because there is a bug in the program. If we have a look at the code, what happens here? We have count, which is set to 0, and then I check if count is equal to 2, and then reset to 0. In this ISR, count is incremented. Apart from this, which is a write operation, which is actually unnecessary, the only other write operation to count is in the ISR. However, the ISR is never called within the program. So the compiler does not know that this function is even called. Since this function is never called in software, the compiler sees that this write operation is never executed, hence count will always be 0 from the compiler point of view. That means this if condition will never be true and might be optimized away. That means it is not even in the source code any longer. To inform the compiler that there is a function that actually changes the value of count without being called, we add volatile to the data type definition. Again, this volatile informs the compiler not to optimize count because there are functions which are not called in software but through interrupts, which have a write access to the global variable. Okay, let's recompile and let's try it out. And as you can see, the LED starts blinking every 2 seconds. That's all what I have about Volatile. In the next session, we are going to talk about internal and external interrupt sources. There are several interrupt sources, such as internal and external interrupt sources. Internal interrupts are caused by the internal periphery, such as timers, arithmetic exceptions, or when a communication is complete. So far, we only discussed interrupts caused by timers. There are more interrupt sources, and we will come back to specific interrupts when we talk about the other units and functionalities that the ATmega 328P offers. In contrast, external interrupts are caused by external periphery and signals that are detected by the pins. Let's talk about those external interrupts a bit more. Here is again the pin layout of the ATmega 328P. As you can see, almost all pins can be used to detect external interrupts as indicated by the PCInt, which stands for Pin Change Interrupt. In addition, PC6 can be used as a reset interrupt and PD2 and PD3 as interrupt 0 and 1 respectively. So how can these pins be used as an interrupt? First, there are 3 pin change mask registers, each of 8-bit in size. PC mask 0 till PC mask 2. All 3 into 8, that is 24 pins that can issue an interrupt request, have a dedicated bit in one of those registers. Secondly, there is a pin change interrupt control register, also called PCICR. The 24 pins are grouped together, forming 3 groups in total. PCInt 0 till 7 form group PCI0, PCInt 8 till 14 group PCI1, and the remaining up to PCInt 23 are in the third group, PCI2. Let's have a look at an example. Here we have PC mask 2, which controls the PCInt 16 till PCInt 23. If we want, for instance, PCInt 20 and 21 to be able to issue an interrupt, we have to set those 2 bits to 1. In addition, we have to enable the group in which PCInt 20 and 21 are located. In this case, it will be PCIe2. And the global interrupt requests need to be enabled as well. Let's have a look at the interrupt vector table. The problem here is that not the pin issues the interrupt, but the entire group. As you can see here in the IVT, there are 3 entries for the pin change interrupt request, 1 for each group. That means if, like in our case, 2 pins can issue the interrupt requests, that is PCInt 20 and 21, they are in the same group, and if either of them registers a pin change, the ISR for PCInt 2 is being called. However, we do not know what pin caused the interrupt request, PCInt 20 or 21. If that information is important, there are 2 options. Either implement a software solution in which the current pin state is checked against the previous state, or select the pins in such a way that they are in 2 separate groups. Here, the current value of pin D is stored in a global variable state. The interrupts at PCInt 20 and 21, which are pin PD4 and PD5 respectively, are configured accordingly. This is not shown here. Let's say a pin change at PD4 has been detected and the ISR is called. That means that PD4 is set by now, since the port has been initialized with all bits set to 0. So the pin D register can have a value of 0, 0, 0, 1, 0, 1, 1, 1 if PD0 till PD2 has been used somewhere else in a program. important is that PD4 is set. The previous value of pin D, that is the global variable state, has all bits set to 0. The XOR will point out all differences as we used it before to toggle the LED, making it blink. After the XOR, this will be stored in the variable change. Now we check if the bit at PD4 is set, and for that we AND it with the bit vector pin D4, which is 0, 0, 0, 1, 0, 0, 0, 0. And this results in 0, 0, 0, 1, 0, 0, 0, 0. If this result is not equal 0, then pin D4 has changed. If it is 0, then PD5 has changed. We do not have to AND the variable change with the bit vector of PD5 because there are only two events that can call the ISR. That is the pin change of PD4 that we have checked by now, or a pin change of PD5. If it's not PD4, then it has to be PD5. Also, please note the order. At the beginning of the ISR, pin D is read immediately. There is a slight chance that while the CPU prepared to jump to the IVT and then to the ISR, that the pin changed again, and hence pin D has a value that is incorrect. Imagine that while the CPU jumps to the ISR, pin PD4 has changed again. Hence pin D will be 0, 0, 0, 0, 0, 1, 1, 1. Therefore, this pin change is not detected, and it is assumed that PD5 caused the call to the ISR. To minimize the changes, we read the value as soon as possible and do not use pin D later, but work with the variable current value. However, if you would like to remove even that uncertainty, you have to use two different pin change interrupt groups. Also, please note that while the ISR is executed, no other interrupt request can occur and therefore interrupt the ISR. So even if PD5 changes while handling PD4, it will be handled after the ISR completed the instructions for PD4. Later, more about that. Interestingly, there are no software interrupts available in the ATmega. However, there is a little trick to get those software interrupts anyway, if they are needed. And that is when the pin is configured as an output and to cause an interrupt when a pin change occurs. Here in line 15, you can see that we toggle that pin, which will cause that the ISR is executed. If that is useful is another question. As an alternative to configuring the pins to cause an interrupt, the developer could have turned off the global interrupts, call the function doSomething, and reactivate the global interrupts. It saves the pin and configuration overhead. However, in this small example, the interrupts can be removed entirely without changing the program functionality. To complete the session about external interrupts, we also need to have a look at those special ones represented by int0 and int1. Usually, a pin change interrupt is issued if the pin changes its state as the name suggests. It does not matter if the pin state changes from low to high level or vice versa. Sometimes, however, we would like to know only those changes from low to high or high to low and forget about the other toggle. Obviously, that functionality can be implemented in software. However, why would we if we have hardware support to do exactly that? Let's have a look at the EICRA, which stands for External Interrupt Control Register A. As you can see, it can be configured to issue an interrupt at any change, like the normal pin change interrupts. But it also allows a more fine-grained configuration of issuing the interrupt only at a falling edge or rising edge of the signal. After that is configured, the local and global interrupts need to be activated and the developer is good to go. Okay, that's all about external interrupts. In the next session, we are going to talk about the priority of interrupts. In this session, we will talk about the priority of interrupts in case they happen at the same time. Have a look at the following code example. We have a timer and a compare match interrupt is issued if TCNT equals both OCR1A and OCR1B. In this case, the values to compare TC and T are the same, so both interrupts happen at the same time. But which ISR is being executed first, since both ISR cannot be executed at the same time? The solution is quite simple, and it is in the interrupt vector table. The lower the vector number, the higher the priority. Hence, the reset has the highest priority. In case of our competing compare match units, timer 1 comp A has priority over timer 1 comp B. Quite simple. However, the interrupt of timer 1 comp B is not forgotten. It is just deferred and its ISR is executed as soon as the CPU finished the ISR for the compare match unit A. Hence, both ISRs are executed sequentially, starting with timer 1 comp A. That was a short session about the priority. In the next session, we are going to talk about a few details what actually happens if an interrupt occurs. So what happens when an interrupt occurs and what is the overhead? Okay, first the program counter is stored so that the CPU knows where to continue its execution once serving the ISR is completed. Secondly, the CPU jumps to the interrupt vector table to figure out the address of the ISR in the program memory. That jump takes 4 clock cycles. During that jump, global interrupts are deactivated, so while the ISR is executed, all interrupts are deferred and the ISR itself is not interrupted. After figuring out the address of the ISR, the CPU jumps to the address of the first instruction, taking 3 clock cycles. Generally, this is an unconditional jump instruction that we have seen at the beginning of this chapter. After the ISR is served, RETI is executed. That is a special return instruction which jumps back to the saved program counter while reactivating the global interrupts. we have the same counter example as before, but this time the developer incremented the OCR1B by 1. That means while the CPU is handling the interrupt of the compare match unit A, the interrupt request of the compare match unit B is issued. As discussed before, the ISRs are executed sequentially. However, if the developer requires that an ISR itself can be interrupted, the ISR accepts another parameter, and that is ISR no block. That means that the ISR of timer 1 comp A can be interrupted now. This is called a nested interrupt. So what happens here? While the mechanics for invoking the ISR of timer 1 comp B remains the same, the global interrupts are not deactivated for the ISR of timer 1 comp A. That's all about nested interrupts. In the next session, I will show some coding mistakes, especially when handling interrupts. Okay, here is an example of what not to do in an ISR. Please refrain from using delay functions in the ISRs. The reason is that while the CPU serves the interrupt, global interrupts are usually deactivated. That means if other events occur, they are deferred. If those events occur multiple times while the CPU is still in this ISR, only the last interrupt request is being served once the current ISR execution completes. All previous events are lost. Another example is in the ISR for timer 1 comp B. It contains a waiting while for the ADC, which will be handled later in the course. While the CPU polls the ADC is ready bit, it cannot do anything else. Many times, polling can be replaced by another interrupt. And in case of the ADC, there is actually an interrupt that the ADC can use if it is ready. So it would be better to start the conversion in timer 1 comp B and have another ISR that is executed once the ADC is ready. These are the major mistakes that I have seen so far. Please remember that interrupts are like atomic, that is uninterrupted, high priority function executions, so keep them short and crisp. That's all about good coding practice. In this chapter, we did quite a bit and learned about interrupts in the ATmega. We talked about the ISR, how to share the code in case two interrupt sources should execute the same ISR. We also talked about empty ISRs and the catch-all ISR called bad ISR. We saw that interrupts need to be activated globally and learned what the data type attribute Volatile does. Further, we had a look at the interrupt vector table and saw which interrupt is executed if two of them happen at the same time. Towards the end of the chapter, I showed you some examples of how not to write an ISR, that is, long waits in the ISR or calling the delay function. So, since you know how to use interrupts by now, I suggest to have a look at the exercise which uses everything that we had so far, from timers to interrupts. After that, what will be the topics in the next chapter? We will start with communications, since it is good to communicate your results of, for instance, the temperature sensor. We will talk about what communication protocols are supported and explain the differences. See you in a bit, and thanks for watching.